Okay, we'll see now the solutions of AECPRE second one. The first part we just wanted to know, so what is the value of Vs that can be used so that we can effectively use this resistor safely. So this resistor is having some resistance value and it is also associated with a wattage along with this resistor. So this is a quarter watt resistor. Since it is connected across this Vs, the power dissipation is given by V square by R. We know what is the maximum power that it can dissipate, which is 250 milliwatt. So which is equal to the voltage across this divided by the resistance. So from which we know that if the voltage across this is less than 1.58 volts, so then the power dissipation will be less than 250 milliwatt. So then it is safe to operate. If the voltage is more than this, then the power dissipation increases beyond 250 milliwatt, which is the rated power dissipation of this. Then you are in trouble, or when you the resistor will heat up and then finally it will going to burn out. Similarly, of course, this is we are asked to find what is the value of minimum R that you should use it so that this is safe to operate. So again, using the same analysis, so we are trying to find the value of R so that it is safe to operate. The value of resistance can be anything more than 6.4 kilo ohm will be safe with a voltage of 40 volt. Similarly, of course, we did the same thing for this. So we actually found out what is the series resistance. I think you can able to understand this one. So if you have 100 volt across which you have two resistors connected, since one of them will going to dissipate 9.8 watt, which is far greater than its wattage, then it will going to burn immediately. The circuit will become open. This may not, of course. So this will, since it is 98 milliwatt, which is less than 250 milliwatt, this may be safe. When this burns, so the overall current stops, and this will also nothing will happen to R1, but R2 will going to burn out. On the same lines, it is this. Of course, we found that power dissipation of R2 is 4 watt. This will burn, and the moment this burns, of course, the current will be keep flowing through this R1, which is hardly 40 milliwatt is the power dissipation. Lines will be keep coming. It is not a safe circuit because this is going to burn very quickly. This is interesting. We are asked to find out what is V0. You have a capacitor resistance. So let us spend some time with this. I think there is no need to simulate all this circuit, which you can do. Can connect this circuit, try to see what is the power dissipation, and maybe in simulation you may not be able to make that power dissipation restriction, so nothing will happen. Maybe when you come for demonstration classes in September first week, we will literally see this resistor burning and this is safe, and maybe this resistor burning and this is safe. We'll just see all the stuff. So that's worth observing a resistor burning. So in a specific case. Let us come to second part of the solution. So where there is a resistor and a capacitor involved, and you are asked to find what is the output voltage here. In the second case, you are again asked to find what is the output voltage here. In the two cases, in this particular circuit, you are asked to find out what is the frequency at which the output voltage becomes V0 by root 2. This is one circuit, this is a second circuit. So this is a bit new one to you people. Let us try to understand. Of course, let us spend time in doing the simulation also to understand what is the effect of this capacitor and why the frequency is now coming to picture. Instead of a sine wave, if you use a DC signal, what happens? If you use a battery, what happens? All those stuff we'll see in the simulation. Okay, for that let me just open this, turn on this video. Okay, now let us assume that we have a circuit which is having a source, and we have two resistors R1 R2, R2. So this assume that this is 1 kilo ohm and this is 10 kilo ohm. This assume that this is V0 and this is V in plus minus. Let us assume that this is a DC source of 10 volt, DC source of 10 volt. And what is V0? V0 is nothing but current flowing through this multiplied by the resistance R2. Then what is the current flowing through this? Current flowing through this is nothing but the input voltage divided by the total resistance R1 plus R2. So that is the current, because if you consider this as the current, so what is the overall voltage? Overall voltage is V in. So what is the overall resistance? It is R1 plus R2. So we are assuming a current of, so just write a KVL for this. Shall I write, this is plus minus voltage rise, there is a voltage drop I into R1, so there is one more voltage drop I into R2 equal to 0. So can I write V in is equal to I R1 plus R2. Therefore what is I? It is V in by R1 plus R2. So that's what is this I have written here. So in place of I have written V in by R1 plus R2 multiplied by R2. So what is V in? Now it is 10 volt multiplied by what is R2? R2 is actually 10 kilo ohm. So this is 10 plus 1, it is 11 kilo ohm. So this is the value. So what you can do now is, it is 10 into 10 divided by 11, because kk will go off. So I can simply write it as so on. So it is 9.09 volt. This is when it is a DC signal. So assume that I don't have a DC signal, so it's a AC signal, which is assume that when I say AC, it's a sine wave. It's a sine wave of amplitude 10 volt and frequency, assume it as, so this is separation between this is, if it is 1 millisecond, that is, if this time period is 1 millisecond means, then frequency is 1 over time millisecond. Now it is 1 over 1 millisecond, which is not but frequency will become 1 kilohertz. 1 kilohertz. So can I write it as 10 sine 2 pi 1k t. So this is my frequency. We know that it is 2 pi of t. So it is sine 10. So shall I write it as 10 sine 2 pi 1000 t. Now the frequency is 1000 hertz. This is 10 is the amplitude and this is sine wave. So this what is this. If I apply this signal to this, what happens? Now naturally, instead of this 10 only, now it is 10 sine so also. So it is 10 sine 2 pi f t, where f is 1000. So what will be this then? The output voltage will be 9.09 sine 2 pi 1000 t. So this is my V0. No change. If you change this from 10k to 1k, then this will become 1k by 2k, then this will become 5 sine 2 pi so on so. So now you can see this quantity remains the constant, remains as it is, only this will be keep changing, this will be keep changing. This is fine. So now you can see this is keep changing. So assume that when R2 is equal to 1k, this is 5 sine 2 pi 1000 t. When let me just write it is when R2 is 10k here, when R2 is 1k. When R2 is 100 ohm, so how much is this is? So if it is 100 ohm, so I'll replace it by 10 into 100 divided by 1000 plus 100. So can you see now it is 0.909 sine 2 pi 1000 t. This is if I change the value of this R, so at same frequency. Now what I'll do, I will use a capacitor. I'll use a capacitor now. So instead of using two resistors, I will use one resistor and a capacitor. So this is C, this is R. So let me now use, let me use a source Vn. So I want to measure V0. So let this be 1 kilo ohm, let this be 1 microfarad. So for some instance, let us see what happens if you use Vin. Vin is DC of 10 volt. Again, same, let us use same DC ones, and then we'll use this sine source of so and so. Let us see what happens. Now this is a capacitor. So we know that capacitors will have resistance to the current flowing, which we say it as reactance of a capacitor. So we know that reactance of a capacitor, which is nothing but Xc, is given by 1 over J 2 pi Fc. So there is a J term associated with this reactance, which is nothing but 2 pi Fc. 2 pi Fc. What is this F? It is the frequency of the signal that is passing through that, and C is the capacitance of that capacitor. Now we know that for DC frequency is 0. When frequency is 0, then what is Xc? It is 1 over J 2 pi 0 into C. Whatever is the value of C here, since frequency becomes 0, 1 over 0 is infinity. Now this is infinite. So what do you mean by infinite? So capacitance, reactance offered by a capacitor is infinite, means it is open circuit. So now you can write it so. Can you see now this is open circuit? So this is a DC source which is having some 10 volt. So then this is 1 kilo ohm. Then what is V0? When it is open circuit, the current is 0. The current is 0. Why it is 0? Because there is no closed path. So when current is 0, then how much is the drop here? Drop is also 0, because I into R. Since I is 0, whatever is the value of R, I into R is 0 across this. When there is no drop, then whatever is the voltage that is there, 10 here, same voltage comes here. Because you know that if you measure with respect to ground, a 10 volts will be here. Since there is no drop, because this is open circuit, how much voltage you will get here? You will get same 10 volts because there is no drop. So V0 is 10 volt for a DC signal, irrespective of the value of C and irrespective of the value of this R, because there is no current. So when there is no current, I is 0. So I into R is 0. The V0 is same as the input voltage. So I can write V0 is equal to Vin for a DC signal if my capacitor is there over here. Now what happens if you have it this way? See, now I have same capacitor, which is now 1 microfarad, same resistor. I want to know what is V0. So this is now plus minus. It is now Vin. Let us assume again same volt, 10 volt DC. So what is this is now for DC? It's open circuit. So now you can see it as open circuit. This is not there. So when it is open circuit means infinite resistance. When the resistance is infinite, so then you have some resistance here. You have some resistance. So you have infinite resistance and there is some resistance. So you have, what is this drop now? When you have infinite resistance, even a very small current flows, everything is dissipated here. So all 10 volts will be dropped here. So 10, everything is dropped here. How much you'll have? You'll have 0 volt. So where is the 10 volt gone? It's now stored in this capacitor. The capacitor holds all 10 volts. The output voltage is 0. Let's do that here and then try to. Okay, what I'll do, I will take out this. I will take out this also. Let me take a new circuit. So I want to have a capacitor. So I want to have a resistor also. Control R, put it here. You take a source. Now let me use this as a DC source. Now this is a DC of magnitude 10 volts. I will do the connection. I'll start from here, go all the way, come down. Okay, now this, even though I'm just not stopping here, because as a component comes, it is going to break itself. Now this is 1K, this is 1 microfarad, 1 U, you say it, U is micro now. and then put a ground. Where is ground? It is, type it as G, it will come. Put it here because it's get connected now. If you want to have clarity, M means it will going to move, and then take again wire, W is wire. Now you do the connection. So we are done. Now I want to do the analysis. It is now again transient. So transient is what? Okay, go up to maybe 10 millisecond. Oh, and that is becomes 0. 10 millisecond, 0, and then 1 microsecond is my. Okay, if I run, so as per expectation, what should happen? This is my circuit. When this is 0, I have to get output voltage as 10 volt. Whatever is the input, same should be the output. So now let me run. See the input. So I can label this as, you can see this is input voltage N001. So let me label this. I can label the net as V in. Let this be V in, let this be V out. So let me name it as V out. Okay. How much is V in now? V in, can you see now? Okay, let me just take out this. Now if I place this, if I run, you can see now, can you see this is coming as V in? The moment you label that node as some XYZ, the same name will be coming. So as per this, since it is DC, no current will be flowing here. So if you see the current also, you can see the current is actually in terms of, this is actually 0 ampere. So no current is flowing. So since no current is flowing, no drop across the resistor, so that V out will also be 10 volt. See how much is V out? V out is also 10. V in is also 10. Can you see? This is V out 10 volt. V in is also 10 volt. So how much is current? Current is 0. Current is 0 ampere because this is a DC. So that's what we said here. Did we say the same thing now? So since the impedance is infinite, current is 0, so no drop, output is equal to input. That's what we saw. Now let us interchange this resistor capacitor. For that I will move it. I will take this, put it here, I'll take this, and I'll do Control R for rotating. Let me place this here, and let me do again Control R. Let me place this here. Now I will do this, sorry, I will wire it because this is not connected. Let me connect this to this. Okay, done. If I run now, what should happen? The entire voltage should drop across this capacitor. I should get 0 here, and you can see now, the moment you do that, can you see what is, okay, let me just redo it. What is V in? V in is 10. See here, it is 10 volts. So how much is V out? V out is 0. Okay, you can see V out is actually femtovolts. Femto means 10 power minus 15, which is 0, which is, you can treat it as 0. You can see input is 10 volt, output is 0, Then where does the entire voltage gone? The entire voltage is there across capacitor. You can see, if you see it across capacitor, so that's what I'm seeing here. This is across capacitor. Can you see it is V in minus V out? Can you see this is V in minus of V out? It is 10 volt. So entire voltage is there stored in this capacitor, which is now 10 volt. So that's what we discussed here. Entire voltage is across this capacitor. Fine. This is when you have this source as DC source. Suppose if this source is sine source, let us see what happens. So let us redo it. So when I say redo, let me just, okay, what is that? Make this controls add. Okay, now this is gone back to the same circuit. Now instead of this, let me use a sine source. So let me not use a DC now. Okay, let me take out this. Let me use a sine source. There is no DC offset. You give 10 volt amplitude. Let the frequency be 1000 hertz. That's it. Okay, all these things not to specify. Now I have a sine source of 0 DC voltage and 10 volt amplitude and 1000 as the frequency. Now let us actually find out what is the waveform that you're going to get and all those stuff. Let us do the calculation, then verify. Shall we go here? Now it is no more a DC signal, but it's a AC signal. So now let us try to find out how much is the output voltage. So again, what is output voltage? We know that expression for V0. So let us name this. Now this is no more a 0. So let me say it as some XC. So now is my output voltage. So what was the output? Okay, output voltage shall I write it as I into XC. So what is I? I is nothing but the overall resistance. Overall resistance is V in divided by R plus XC. Correct? This is the current multiplied by XC. This is XC. But what is XC? XC is 1 over J 2 pi FC. So what is F, what is C? We know the value of F as 1000, C is equal to 1 microfarad. You know all those things. So what we'll do now, it is V in, it is 1 over 2 pi FC, correct? So it is now J, in the denominator you have a J also, divided by, so how much is R? It is 1000, again XC is 1 over J 2 pi FC. So for this, shall we write as, so I can take J outside and can, the numerator I can write as minus J. How much is this? It is 2 into pi into 1000 into C is 1 exponential minus 6. 1 over that is actually 159.15 ohm. This is now, so V in is minus J, it is 159.15 divided by, how much is this now? This is actually so now shall I write it as, so now it is 1000 minus J 159.15. This is what you have as the components, Now it's actually 0 minus so and so, correct? 0 minus so and so. Now this is, since it's a complex quantity, so you have a complex quantity. When you have a complex quantity, it will going to have magnitude and the phase. So this V0 will have some magnitude and phase also. So what is the magnitude and phase of your sine wave? Suppose, of course, the input voltage has got a magnitude of 10 volt at a frequency of 1000 hertz. Phase is 0. But here V0 will have some different amplitude, maybe X. The frequency will be again 1000. The phase will be something other than 0. It will be either leading or lagging depending on the capacitor position. Now, so we have these as the parameters available. Now I need to find what is V0 expression. Just a minute. Okay, we will see what is. So now we have this as V in. So this is a complex quantity. I need to find the magnitude and phase of it. So what is the magnitude and phase of it? So we know that, suppose if I have it as 0 A plus JB. So what is the magnitude of this? So magnitude of this is root of A square plus B square. What is the phase of it? It is tan inverse of B by A. So where B is the coefficient of your imaginary quantity, A is the real quantity. So what is the point, what are the parameters you have? You have it as 0 minus J 159.15. So what is the magnitude of this? So magnitude is again A square. A square is 0. What is B square? So this is B. Actually 159.15 whole square. So So what is the outcome of this? This is nothing but 159.15 only. So magnitude is 159.15 only, but what is the phase? Phase is nothing but tan inverse of minus, because I need to consider this negative also, minus 159.15 divided by 0. So it is tan inverse of minus infinity. So we know that tan inverse of minus infinity is actually minus 90 degree. So now this is minus 90 degree. So this is the magnitude and phase of this XC at 1000 frequency. Now I should know what is the magnitude and phase of this. So what is the magnitude and phase of this? So magnitude of this is under root of, okay, now what is the magnitude of this? So magnitude of this is under root of 1000 square plus 159.15 whole square, so on. So shall I find that? It is 1000 square plus 159.15 whole square, sorry, not whole square, it is square close equals, can you see it is now 1002.58 at an angle. What is the angle? Angle is tan inverse of b by a. So this is tan inverse of, so it's again negative angle. So now, so it is tan inverse of minus 159.15 divided by 1000. It is this. It is minus 9 point something. It is minus 9.04. If it goes up, that will become plus. So shall I make it plus 90? Can you see the overall phase of the output voltage is 80.9? Okay, it is minus 80.95 degree. Now you can see it is minus. Minus means it is phase lagging. What the magnitude? Magnitude is 159.15 divided by 1002.5. Is it correct? So can you see the magnitude is 1.157. This is the magnitude, of course, V in times so and so, V in times so and so. So ultimately, so what is the output voltage now? The output voltage now is, so this is what is the expression what we have. This is the expression what we have now. So now V0 is equal to V in times 0.15 at an angle minus 80.95 degree. So what does this actually mean now? This means, so this is actually 10. Is it not 10 into 1.5? 0.15. Is it not 1.57 is the magnitude? What is the, it is sine 1000, okay, 2 pi 1000 t plus, sorry, minus 80.95 degree. It's actually lagging. It's actually lagging. Suppose if I rewrite that, so what is V0 now? V0 is equal to, okay, 1.57 sine 2 pi 1000 t minus 80.95. It's like, okay, it's omega t plus or minus 5. So this is phase, this is phase. So here in this case it is negative. Let us try to see what happens to the simulation. Let me go back here. This is what we have done. If I run now, so if I run now, okay, I will take out all these parameters. Now I will run. This is my Vin. Can you see there is a sine wave of so and so frequency? Can you see this is V0? Can you see this is V0? Can you see V0 is lesser than Vin? Okay, let me change the color. See now? Now, if you see V in peak is 10 volt. V in peak is 10 volt. Can you see this is 9.999? This is 10 volt. Can you see what is V0 peak? Can you see what is V0 peak? Can you see V0 peak is somewhere around 1.57? That's what we expected Don't we see this? This is what is V naught expected, because this is how we got it. This is my magnitude 159.15 by 1000, so on. So this is due to XC by R plus XC. So this by this, it's like, okay, whereas in case of resistor it was so simple. It was R2 by R1 plus R2. Now in place of R2 you have XC, in place of R1 you have R1 only. So the magnitude has changed. Magnitude has changed from input of 10 volt. From input of 10 volt it has become, okay, 0.157 multiplied by 10, that will become 1.57. That's what you are seeing in the simulation also. But can you see, is this peak is not at the same point as this peak? Can you see there is a phase shift? So when I say phase shift, okay, let me show you the difference of that and this. So it's actually how much? It's 159 now. Let me show you one thing. I will replace this capacitor by a 159 resistor, 159 ohm resistor. Then the magnet will be 1.57 volts. You can see the phase will be same as this. So what I'll do is I'll just show you what I'm trying to do. If I take out this if I take out this capacitor, I will put a resistor now. What should be the resistor value? Let the resistor value be as that of your XC, which is 159.15. If I replace that capacitor by a resistor which is offering same resistance as that of the capacitor at frequency 1000 Hertz, then you can see the difference. Can you see? This is again 10 volt as your input, because input you did change. Input you didn't change. You can see input is still 10 volt here. Input is 10 volt here. So I'll go to the peak. I'm just zooming it here. Can you see it's almost 10? See the output? Can you see the output is 1.5? Okay, it's 1 point. Okay, 159. Okay, more importantly, what I'm trying to show here is the input and output are in phase. So this is in phase. So I'll show you what you mean by in phase. This you can see. Can you see these peaks are coming at same point? These peaks are coming at same point. If I write it on this sheet, when I say in phase, if this is my input signal, if it's a purely resistors, then I will have the peak and this will be coming at the same point. They'll be coming at the same point. You can see they are coming at, sorry, this is how it comes. Maybe of lesser amplitude, that depends on R1, R2, but the phase remains the same. No shift in the waveform. But the moment when you make it by a capacitor, so how do I do that? Control side. Now the moment when you put a capacitor, if you run it, can you see this is lagging? Can you see this is your input peak, output peak is coming here. This is actually lagging by how much? It is lagging by 80. That's what is here now. It is lagging by 80.9 degrees. Negative means lagging. It is lagging by 80.95 degrees. That you can very clearly see. Now what I'll do, I'll not do a single frequency. I'll do it for I'll change the frequency of this from very small value to very high frequency. Let us see that phase shift of 89, because now it is difficult to measure the phase shift. So I will change the source from sine to an AC signal of magnitude 1. Let me show you that phase shift of minus 80.9 degrees. So this is done. I will change the analysis to AC analysis. I will make a decade sweep. Okay, this I will explain later. Let me start from 10 Hertz, go up to maybe 10,000. Okay, I'm doing a different analysis now. So now it is the AC sweep. So let me put it apart. Okay, this I just want to move this so that you can have clarity. If I run now, you can see this is magnitude, this is phase, this is phase. So at 1000, how much is the phase you're expecting? At 1000 radian, at 1000 hertz, the phase shift is minus 80.95. Just keep an eye on this. Let me change this output. Okay, I'll move this cursor now. I'll just run it now. Okay, what I'll do now is, okay, let me run this. If I move the cursor on this one, where is my cursor? Just a minute. I will run. If I run, I can move the cursor. Okay, what happened? Okay, just a minute. I will take out this. How do I take out? Go here, cut this. You run it again now. I'm running it. So let me see this wing out. See now. See, you go to a frequency equal to 1000 hertz, the phase should be minus 80.4. Just keep an eye on this. What should be the frequency? 1000. That's what this says. So at 1000 hertz, the phase is minus 80 point something. So let me have an eye on this. Let me keep moving. Can you see the phase is now, sorry, frequency is 1 kilohertz close to. We go to 1 kilohertz. Are you there? I'm almost there. Can you see it's almost 1 kilohertz? Maybe you can zoom it further. Can you see you are there at 1.0003 kilohertz? What is the phase? Minus 80.9. What is the phase you expected? You expected the same phase, minus 80.95. So what does this mean to say is I can able to see there is a phase change in the signal. It will not be in phase as in case of a resistor. So in case of resistor, they will be in phase. In case of capacitors, sometimes it will be lagging. When I say lagging, this peak will come after some time. This peak will come after some time, so it lags. So there are some cases where this peak will come early. So this I call it as lead. So this is phase lead. This is lead. This is lag. So in this particular circuit, even though of course you can change this to 1K. Okay, this is 1K. Okay, here we had it as 100 ohm and 0.1. Again, for same one frequency, you should get the magnitude should be how much? Okay, this is C part. Okay, for this you want to get, you should get as 9.99. I didn't mention the phase here. This is just the magnitude of the output voltage, which is 9.99 if this is 100 ohm and 0.1 microfarad, which I can show it now also here. So what I'll do, I'll go back to this. I will again do Control Z. Okay, this is now same. Instead of this, I'll make it 100. I'll make this 0.1 micro. What should be the amplitude? Amplitude should be 9.99. You can see this is, see now this is output. Let me give the input also. Can you see input and output are almost coinciding? You can put it in other pane. This is my output. If you go to the peak of it, just zoom it, go to the peak, or the peak, you can see it is 9.99. This is 9.99. If you go to the input peak is almost there at, where is the other one? Wait, I'll show you. This is the other one. Okay, let me this is moving on output, which is 9.99. This is moving on input. Can you see it's almost this can you see this is V input, it is 9.999, which is almost 10. Can you see this is output, which is as per our calculation, sorry, as per our this calculation, output should be 9.9 sin omega t. Of course, we didn't find the phase. You can certainly find the phase as we did over here, where is that? As we did over here. So you can make this as 100 ohm, make it as 0.1 microfarad, find out at 1000, okay, what is this magnitude and phase. So you will certainly see all those things. So, but you can see they're almost in phase. So there is no much change in the phase shift. It is for this value of R and C, you don't have a phase shift. If the value of RC changes, then naturally the phase shift will change. Even if the frequency changes, then also phase shift will change. Because the phase shift is purely decided by, if you can see this, the phase shift is decided by this quantity. Okay, this quantity. So can you see this quantity will going to change with respect to frequency as well as the value of C. So as this F and C changes, then this will change. When this will change, phase will change. When phase changes, then shifting of your waveform will also change. Okay, so get used to such type of interesting things. So of course, it takes some time to swallow these things, but this is how it matters. So now, if you change the frequency of the signal, then this reactance will change. Once the reactance changes, both magnitude as well as phase, both will change. So we just did it for 1000 as the frequency. If you change the frequency from 1000 to 10,000 or from 1000 to 100, then this will certainly change, because that frequency will change both magnitude as well as the phase. So this magnitude will not be always 0.157. That will be keep changing depending on the value of frequency. So that's why we say reactance offered by capacitor is depending on frequency. It's a frequency dependent component. Its reactance varies with the frequency of the signal. Thank you.